Okay, so as previously promised, here's a couple of questions to do with the interference with Young's double slit, single slit, as viewed from a higher level, additional higher level perspective, a topic 9 perspective. First question is a multiple choice question from the November 2017 paper. Monochromatic light, so light of one wavelength, as you would get from a laser or possibly from a sophisticated sort of filter. Monochromatic light is incident on two identical slits to produce an interference pattern on a screen. So incident on means that it's hitting the two slits and light is passing through those two slits. One slit is then covered so that no light emerges from it. What is the change to the pattern observed on the screen? Okay, so you basically have a two slit interference pattern as is described. Then you cover up one of those slits, so what will remain will now be single slit diffraction pattern, the only thing you can see. So if you haven't yet, pause the video, see if you can have a look at the options and see what you think it is. Okay, so assuming you've done that, what are your options? Fewer maxima will be observed, the intensity of the central maximum will increase, the outer maximum will become narrower, or the width of the central maximum will decrease. Well, I simulated both of these using the Wolfram Alpha demonstration, and this is what you get. So you're moving from the two slit diffraction pattern to the one slit diffraction pattern, or the two slit interference and diffraction pattern to the one slit diffraction pattern. So which of these two are true? Well, fewer maxima will be observed. Straight away, that is true. You've got, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 maxima you can see on the two slit pattern. Maxima of different intensities, but they're still maxima. Whereas on the right hand side you've got, well, just a one central and a couple of satellite maxima. The intensity of the central maxima, that's one I would say is true, but it's always worthwhile looking at the others just to see and to double check. So is the intensity of the central maximum increase? No, it does not. It actually is the same, the peak intensity. The outer maximum will become narrower. No, they don't. They become wider as you go from two to one slits. And the width of the central maximum will decrease. No, in fact, it increases. It goes from being the narrow two slit diffraction pattern, interference pattern, to the much wider one slit diffraction pattern. Okay, so that's one multiple choice. Let's look from the 2019 made paper at a more involved question. The first part is actually not really from this little section, but we'll look at it anyway. You have again two slits of negligible width, a distance d apart. So initially, at least, we don't have to worry about the diffraction because it has negligible width. A screen is placed a distance big D from the slits. So immediately you should be thinking, what equation am I going to be using here? But I say the first part of the question doesn't actually go into that. It tells you that initially the lower slit is covered, so you only have one slit, and the intensity of the light at M due to the upper slit alone is 22 watts per meter squared. The lower slit is now uncovered. Deduce the intensity at M. Well, at M is equidistant from the two slits, so you'll have constructive interference. If you have constructive interference, the two waves will add. So whereas previously you had wave of one amplitude, you will now have twice the amplitude. So with two slits, the amplitude is doubled due to the constructive interference. That's the amplitude. Now, what you have to remember, it's in the data booklet, is the equation that the intensity of light is proportional to the amplitude squared. So I is proportional to A squared. A squared. So if you're doubling the amplitude, your intensity will go up by 4 times. Your initial intensity is 22 watts per meter squared. Multiply 22 by 4 and you get 88 watts per meter squared. Okay, so we will always remember that relationship. Amplitude squared gives you the intensity. The second part gives you some information. It gives you now the values for the separation, 0.12 millimeters, The value for the distance to the screen, 1.5 meters. Notice the discrepancy there. It says the diagram is not to scale. It's not joking. It's very much not to scale. And the distance from M to P equals 7 millimeters. Calculate in nanometers the wavelength lambda of the light. It's just 2 marks. If it's just 2 marks, then there's an equation, but you don't just quickly plug the numbers in and get the answer, because that would be 1 mark. Instead, you have to rearrange. So if it's 2 marks in a question like this, you pretty much know you've got to find the equation, rearrange that equation to get the variable that you want, plug the numbers in, and that's your 2 marks. So the obvious equation, if you've been looking at the topic, would be the S slit separation equals wavelength times the the fringe separation, distance in this case from M to P, equals the wavelength multiplied by the slit separation divided by the distance. Rearrange that and you get that the wavelength equals the slit separation multiplied by the fringe separation divided by the distance. Plug those numbers in. There's the little trick, is to remember that you've got to convert everything into the same units. In this case, it would make sense to convert it into the SI unit, the meter. So 0.12 millimeters is 0.12 times 10 to the minus 3. 7 millimeters, 7 times 10 to the minus 3 divided by 1.5 meters will give you an answer of 560 nanometers, or 560 times 10 to the minus 9 meters. Okay, so as long as you've got the right answer combined with the right unit, you'll be fine. It's one of those cases where putting the unit isn't absolutely essential, because the IB doesn't worry too much about it, but it really helps to make sure that you're being consistent. Part C says that, okay, we're now going to worry about the slit width. Previously we haven't worried about the actual width of the slit, but now we are. And it increases to a 0.030 millimeters. Everything else stays the same. Suggest why the intensity at P will be less than that at M. Just the 1 mark. Just 1 mark, so it's not a complicated question. Well, what have we done? We've introduced a slit width, so now we've got to worry about the diffraction pattern. And by implication, once we apply this diffraction pattern envelope, then the intensity at that point will be less. So changing the slit width will change the single slit diffraction pattern, and changing the single slit diffraction pattern will have caused the intensity at P to be less than that at M. Certainly wouldn't have increased it or left it stay the same, so it's got to decrease it. Finally, part 2, show that due to single slit diffraction, the intensity at a point on the screen a distance of 28 millimeters away from M is 0. So it's a show that question. So you've been given the answer to be looking for. And it says due to single slit diffraction, so you're kind of told which equations you have to worry about. The equations you have to worry about is theta equals lambda over b, where theta is the angle, lambda is the wavelength of light, and b is the width of the slit. So but looking at the diagram, we can draw theta. It's not to scale, but we can kind of indicate what theta would be there. And we're given the information to calculate this angle geometrically, using trigonometry. So theta equals S, the slit separation, which is now the distance from the M to that point, which is 28 millimeters, and big D over 1.5. Don't worry, we don't have to worry about sine, cos or tan, remember, because we are dealing with very small angles, and that all vanishes or becomes irrelevant. So 28 times 10 to the minus 3 meters divided by 1.5 meters gives you an answer in radians of 0.01867. We can also calculate what the angle should be to the first minimum, which is the theta equals lambda over b. Don't forget, in that equation, theta is the angle to the first minimum, lambda is the wavelength of light, and b is the separation at the the width of the slit. Sorry. So wavelength of light were given earlier 560 times 10 to the minus 9. In fact, you had to work that out, didn't you? So if you'd got that wrong, there would be error carried forward, but hopefully you didn't get it wrong. We'll divide that by the slit width, 0.030 times 10 to the minus 3. Again, make sure everything is in consistent units, and you'll see that that equals 0.01867 radians. So the actual angle that's there is 0.01867 radians. The angle to the first minimum is 0.01867 radians. These two are the same. So 28 millimeters from M is the first minimum of the diffraction pattern. Alternatively, you could have done it in the other direction. You could have calculated what the first minimum angle would be, and then seen if that applies to a screen using trigonometry. So either direction is fine. Both would get you both marks. Okay, thank you very much.